All right, today we're jumping into a really cool topic in Trig, even and odd identities. Now, these are basically powerful shortcuts that are going to help you simplify what look like really complex problems super quickly. So let's kick things off with the big question. Imagine you're working through a problem and you run into something like, say, the sine of negative 30 degrees. What do you even do with that? Does that negative sign just, pop out in front, or does it just vanish? Well, figuring that out is the whole key to what we're talking about today. Now, before we get all tangled up in sines and cosines, let's connect this back to something you've probably already seen in algebra. We're talking about the idea of even and odd functions. So the good news is this isn't some brand new, out-of-the-blue concept. We're just taking an idea you already know and giving it a new home in trigonometry. You probably remember this, right? An even function, like x squared. It's a perfect mirror image right across the y-axis. What that really means is that f of negative x is the exact same thing as f of x. Then you've got your odd functions, like x cubed, which has that cool rotational symmetry around the origin. And for those, f of negative x turns into the negative of f of x. So the whole deal here is that relationship between what happens when you plug in a negative x. Okay, so how does all this algebra stuff apply to trigonometry? Well, the secret, the key that unlocks the whole thing and gives you that visual aha moment, it's all hidden in the unit circle. This is where we're going to see why these rules actually work, so you don't have to just blindly memorize them. And it really all comes down to one word: symmetry. That's it. It's the beautiful, predictable symmetry of the unit circle that gives our trig functions these really cool, special properties. Okay, so let's set the scene. We're starting with a positive angle, we'll just call it theta, right? And we rotate counterclockwise around the unit circle. The spot where we land, that point, has an x-coordinate of cosine theta and a y-coordinate of sine theta. Pretty standard stuff. But what if we use a negative angle instead? So minus theta. We rotate the exact same amount, just clockwise this time. And when you look at it, you can see it perfectly reflects our original point straight down across the x-axis. And here's where it gets interesting. Because we just flipped over the x-axis, take a look. The x-coordinate for both points is exactly the same. It didn't change at all. But the y-coordinate, well, the y-coordinate for negative theta is now the complete opposite of what it was for positive theta. And that right there, that visual, perfectly explains our main identities. Since the x-coordinate, which is cosine, didn't change a bit, we can say that cosine of negative theta is just cosine of theta. Boom, it's an even function. And since the y-coordinate, sine, flipped its sign, that means sine of negative theta is equal to negative sine of theta. And that, my friends, is an odd function. Okay, so now we get the why behind sine and cosine. Let's use that knowledge to build out our complete toolkit, because we can figure out the rules for the other 4 trig functions based on just these 2. And here's the whole shebang. You can see the pattern right away. Cosine and its reciprocal, secant, are the only even functions here. Every other one, sine, cosecant, tangent, and cotangent, they're all odd. This chart is basically your cheat sheet. Now, I know this looks like a lot to memorize, but trust me, there's a super simple trick. Just burn this into your brain. Only cosine and its reciprocal, secant, are even. That's it. Everything else is odd. If you remember that one little fact, you're golden. All right, theory's great, but let's get our hands dirty. We've got the rules, so let's see how they actually make our lives easier when we're simplifying some real expressions. Okay, here's a classic one. You get asked for the cosine of negative pi over 3. Now, you could try to find that negative angle on the unit circle, or you can use the shortcut. We know cosine is even, right? So cosine of negative pi over 3 is the exact same thing as cosine of positive pi over 3. And we know that one. It's 1/2. See? Done. Okay, let's step up the difficulty just a little. Here we have a product. No big deal. We just apply the rules to each piece. Sine of negative theta. That becomes negative sine theta. Cosine of negative theta? That just becomes regular old cosine theta. Now multiply them together, and what do you get? Negative sine theta, cosine theta. Simple.
Okay, now for a really cool one. Look at this thing. Let's apply our rules. Sine of negative theta becomes negative sine theta, but that whole thing is being squared. Then cosine of negative theta becomes just cosine theta, which is also squared. Now here's the magic part. When you square that negative sign, the negative sign just vanishes. So you're left with sine squared theta plus cosine squared theta. And that should be ringing some major bells. That's our good old Pythagorean identity, and it equals 1. How cool is that? We took that messy looking thing and simplified it all the way down to just 1. That's what I'm talking about.
So, I know what you might be thinking. Okay, that's a neat math trick, but am I ever actually going to use this? And the answer is, oh, absolutely. These ideas are actually fundamental to some huge fields that shape our world every single day. Just think about the music on your phone. How does a massive, high-quality audio file get squeezed into a tiny MP3? The answer is something called Fourier analysis. And what that does is break down the super complex sound waves into their basic building blocks, simple sine and cosine waves. Knowing whether a piece of that wave is symmetric, like a cosine wave, or anisymmetric, like a sine wave, is absolutely essential for compressing it efficiently. It's literally the math that lets you carry your music library in your pocket.
All right, before we finish up, let's talk about a super common mistake. It is so easy to get into the habit of thinking that anytime you see a negative angle, you just pull the negative sign out to the front. But that's a trap.
No, don't do it. Just always bring it back to that unit circle in your head. Cosine is the x-coordinate, remember? When you flip a point across the x-axis, its left-right position doesn't change at all. And that's the reason why cosine is the odd one out. That's why cosine of negative theta is still just cosine of theta. It holds its ground. So there you have it. You've now got a really powerful tool in your trig toolbox for dealing with any negative angle that gets thrown your way. The big takeaway here is that if you understand the symmetry of the unit circle, you don't have to memorize, you just know. Which leaves us with one final thought. Now that you've got this down, what other awesome shortcuts and patterns are just waiting for you to find in trigonometry?